So now in this particular lecture, this is just an introduction to what we have done so far and what we are going to do now. So far we saw about the Kepler's law. Then we saw what it takes to define Kepler's law, the mathematics. So that's what we are currently building in. We are currently building all the mathematics that's required to explain Kepler's law, Kepler's three law. Now, then we saw about the reduced mass equation where we take in two bodies and we consider it as one body system, and we continue our further explanation. Then we saw that how a force equation reduces to considering the mass system, which is mu, which is reduced mass system, and we saw the force equation was F vector 2, 1, which is read as F vector. The force on 2 due to 1 on mu, and this is a second order differential equation. And this is a standard force equation just with a change in the mass. Rather than mass m, we now have mass mu. Then we stated that then I explained the difference the r in two bodies problem was a relative separation, as we saw, while the r in one body is the distance between the single point, this is the r in one body equation, the distance between the single point and the central point, which happens to be our origin. Then we saw the constants of motion. The two constants of motion are energy and angular momentum. Now, we saw in two-body problem, the energy and angular momentum are the constants of motion. We saw E is constant because the gravitational force is an internal conservative force. And secondly, L vector is constant because the force is directed towards the center, towards the origin. So the talk about that origin is 0, and we saw about the origin is 0. This implies the L vector is constant. In time. I could have derived this, but it's a waste of time again. But I have also provided this particular equation, why L is conserved in the notes, which I will send it to you separately. And then we saw that this results in a consequence of orbit of single body lies in a plane. This is very important consequence that deals in the central force motion. So it's better when something happens in plane, it is way better to choose what's called as the plane polar coordinates. So which is r comma theta. So as I saw, as I told you earlier in the lecture, that r vector comma t, r as a function of time, or for that matter theta as a function of time, in most cases can't be r as a function of time and theta as a function of time in most cases cannot be found analytically. What does it mean analytically? It's actually a technical term in classical mechanics, but I'll encourage you to think it as a logical equation. So we cannot derive through whatever we have in our hand. So logically we cannot derive r as a function of time and theta as a function of time. Now this is one of the most difficult topics in physics and classical mechanics to say, because we don't have this two equation which we solve normally. I mean, whenever you try to solve a mechanics topic, what do? You try to find the trajectory of the particle. I mean, you have something, or let's say, okay, this is very interesting. So you have something at time t, at time say x1 t1, and after some time the particle is here, which is at distance x2 at time t2. So you try to find the trajectory of the particle. This is what we do. For that matter, r needs to be a function of time. But when you solve Newton's equation, it's a very long equation. Actually, I don't think any text, I think there exists only one text, solves this equation. I mean, how it comes from the Newton's second law of motion. I mean, Newton's law basically. So rather than getting into this, we'll focus what we have in our hand. So for now, just accept we cannot find r as a function of t and theta as a function of t analytically. So our goal, so what we can do is what I can see here is the problem is the time component, right? The dependence on t. So rather than finding r as a function of t or theta as a function of t, I try to find r as a function of theta or theta as a function of r. This may work. I'm not telling this is going to work. We don't know. I mean, I know. But let's give it a surprise. Will it work? Because all I can say is r as a function of t is an equation, theta as a function of t is an equation. So why we can't find this analytically is because the dependence of time. If we can somehow eliminate this time dependence, we can, which is in the form of r as a function of theta or theta as a function of r, we can solve the equation. So our goal, so let me write it over here. Okay. I'm not trying to save paper, I'm just trying to save my wordings because I tend to go in the flow and I miss the concepts, important concepts. I just deviate from the topics every day. So our goal is to find r as a function of theta. So this is exactly what we had left in the last lecture so far in all the lectures, and we are going to continue our discussion to our goal to find r as a function of theta in the next topic.